Today, we're going to talk about the first section of calculus, 4 ways to represent functions. Now, it basically comes down to there's verbal, numeric, visual, or graphical. We're going to go through what functions are, how they relate, and all those things. Function is simply a machine, is how I think about it. All right? And we know that we have an input, and it goes in the machine, and we have an output. We always call the input domain, and we call the output the range. If I take a graph here, I have graphed a function, and it has a domain from A to B, and we'd often do this in notation, interval notation, like this. It includes A, and it includes B for the domain, and we would write that as X is an element of those things. And for the range this time, it goes from f of A to f of B. And it includes those points. And again, remember, if it doesn't include the points, we would just change it to a parenthesis. But it does, so it's a square bracket. And what it is here is this would be like set A, and it assigns exactly to one and only one number in set B. Domain has one output, and that means that a function always passes the vertical line test, which I typically write VLT. Now we'll get into inverse functions later, and those have to pass the horizontal line test and be one-to-one, but a function simply has to pass the vertical line test. So if you have some sort of graph or representation like that, that's not a function. It has 2 outputs for 1 x input. It fails the vertical line test. So again, we know what domain and range are. So let's talk about a problem here. I have a function f of x equals the radical of x plus 2. Now that's a root function, and we should all recognize that from our pre-calculus days. All right, and we're going to have to be able to do the basic functions, lines, root functions, absolute value functions. We'll cover that here later, but today this is a root function, and if we think of, we know the standard root function looks like this. This is the square root of x, and hopefully remember that. We know the inside cannot be less than 0, but this one is shifted. All right, it is shifted 2 to the left. So when I do this, and I have the graph in the red line, is the graph of my function f of x. I know that it starts at and includes -2 because the inside can be 0, and it goes all the way to the right, to everything, to infinity. The range of this function is set at 0 and also goes to infinity. Again, this should be fairly large amount of review. Sometimes students like to write it this way, and that's fine with me. I prefer this. I prefer the variable on the other side, but either way, any of these notations are correct. So how about this function? G of x equals 1 over x squared minus x. That's a rational function because it has a polynomial on top divided by a polynomial on the bottom. All right, so if it's a rational function, one thing we know about rational functions is that you can never divide by 0. So when I see this function, I first want to factor. In calculus, a lot of times, algebra is factoring. Factoring is the algebra. That's what has to happen. And we know that the bottom cannot equal 0. So x times x minus 1 cannot equal 0. We also know that the bottom can be any other number. So in this case, for the domain, x is going to be an element of all reals. Except, what makes this 0? Well, x cannot be equal to 0 or 1. And this is how I would do the notation. Now, your book, I think, will probably do it a little differently. Your book probably does this notation. I'll go down the board a little bit. X is an element from negative infinity to 0, and 0 to 1, and 1 to infinity. And that's also correct. You notice it doesn't have square brackets because 0 and 1 do not work. All right? So let's talk about a piecewise function. A lot of times this confuses students. You have to think to yourself, how does the graph work? And first thing I notice here is f of x equals 1 minus x. Well, actually, I don't see it as 1 minus x, and you shouldn't either. I see it as negative x plus 1. So let's write that in green. And I'll change it on my smartboard. So I have a line, and then I have a parabola, x squared, our standard parabola. And those are happening when x is less than or equal to 1, it's a line. When x is greater than 1, it's parabola. If I take the time to make the graph first, before I do range and domain, it looks like this. When it's equal to 1, going this way, here is the line. All right. When it's not equal, when it's greater than 1 but not equal to, you notice an open dot, and it's a parabola going up. All right. Maybe my parabola could be a little prettier, but it's there. So is it a function? Well, if I draw my vertical line here on the side and start pulling it through, yes, 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 yes. Ah, what about right there? The answer is yes. Solid dot on the bottom, open dot. Only one output. Yes, 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 yes. So this is a function. And again, when I look at it, x is an element of all reals for domain. It can be any number of x. And then if we look here, y is an element. And from the graph we can tell, well, it bottoms out at 0. And it goes to infinity up the y-axis. So it goes to positive infinity. And I just found the domain of a piecewise function. Now, you can do this other ways. This is the way I show it initially. We'll talk about sets and how we can look at the sets of each part of the function. But again, this should all hopefully seem like review. Finally, there's symmetry. And there are two types. We're not going to talk about periodical today, and I thought I'd throw that up right away. We're not going to talk about sinusoid yet. All right? There's a graph of the sine curve, right, of some amplitude and period. A periodic function repeats every so often. We're not going to talk about that yet. What we're going to talk about today is even functions and odd functions. And an even function can easily be described that it reflects across the y-axis. It reflects across x equals 0. The same on both sides. And an odd function rotates about the origin. And I always say it's the same in the first and third. If I rotate this around, it's the same curve down here. First to third quadrant rotation reflects across the y-axis. So, what's that mean? That means, and I think I got to go down a little bit, that there's a rule here. We have these two cases. Rules on the next page. So y equals x plus 7. So I quickly graph that here on the green line, and I got to label my axes, or I would take points off on tests. So there we go. Here it is. Does that reflect first and third quadrant? Obviously not. Does it reflect across the y-axis? No, because if it reflected across the y-axis, you'd have to have this and this, right? So this is not an even function. This is not an odd function. It's neither. All right? So there's always three choices: odd, even, or neither. And we can always prove it, because when you have an even function, we know that when you input the value on the right side of the axis, it's the same, its output is the same as the left side of the axis. It's a parabola. Here's it positive x, well here's negative x. Well, they output the same value of y. This is still a function, passes the vertical line test. It is not a one-to-one function if you're thinking about inversing again. All right? But it is an even function. On the odd function, when we plug in x versus negative x, our output here is a positive number, our output here is a negative. But it's the same magnitude, it's just the sign. Its distance from 0 is the same. So we also have an odd function, and we can prove this. So I have the cases here, and I'll try to leave the rules right at the top. I want you to prove it. Well, To always prove it, we input negative x and see what happens. All right? And when I do that on this function, 5 negatives is a negative, and I get this, and then I factor it out. And here I am. I got f of negative x still on the left side. When I look at this, here's the negative sign. And what you got to catch, and this is hard for students, is I have taken the time to make sure this and this are the same. So I can replace the underlined part with f of x. And the first function, a, here is I. Go up the next function. All right, we always put in negative x. 1 minus negative x to the 4th. Now forget the power, or forget this double negative. Look at the power. 4 negatives is a positive, so 1 negative, that's there, x to the 4th. So I have d negative x. Well, now when I look at this, I don't have to factor out negative because this and this are the same. So I can just write g of negative x equals g of x. Haha, even. And over here I probably should have wrote Okay, what about the last one? You got to guess? When we look at it, students usually see a pattern here. I'll do it in black. H of negative x equals 2 times negative x minus negative x squared. Very careful of order of operations. This is not positive. This is negative. All right? So then I pull out the negative, and here's what I want you to catch. When I pull the negative out, because I see it at negative 2x plus x squared. And I want you to see that this and this are not the same. So guess what? It doesn't work out for one of the two cases. So the third case is neither. I'm going to make a video where we do some range and domain practice and some even and odd practice. The last thing I want to talk about today about functions is we have to talk about them in terms of are they getting bigger or smaller. And anytime we talk about that, we use the independent variable, the x-axis. And we always go to the right. As we travel to the right, we are getting bigger. And we want to look at the graph reading left to right that way. So you notice I put in some points, A, B, C, and D. And what I want to talk about is as you go from little a to little b along the x-axis, you'll see that the curve is going increasingly higher. That's called an increasing function. And then from B to C, as we go B to C, it's getting bigger as you go here. But what's happening to the value of the output? It's getting smaller. So that is a decreasing function. And then we go from C back up to D. And it's increasing again. So I could say this function increases from A to B, and not including those points, and from C to D. So where is it decreasing? Obviously from B to C. The rule here you should know, all right? And you'll see I have a set of x's here. It's increasing. The function's increasing when x2 is greater than x1, in this case, and what? And f of x2 is greater than f of x1, the output. When's it decreasing? Well, the same rule. You want x2 to be greater than x1, but you want f of x2 to be less than f of x1. And if I was to try to move those points, I think I can. I tried to make them a group. That's close enough. If I move these points here, you'll see that I can, well, I guess I have to move everything separately. I can put the decreasing case right over here. All right? And again, it's important to realize we always put x1, and I got it on the wrong side. X1 on the right, x2 on the left, there we go. Okay, x1 on the right, x2 on the left, there. x2 is greater than x1, f of x2 is less than x1, it's lower down, closer to the x-axis. And again, another thing we want to practice. There are lots of problems in the book, you need to practice them, check your answers against the odd numbers. You have to be fundamentally sound with these things. Remember, day without math is like a day without sunshine.